Alright everybody, what we're going to be doing in this video is teaching you how to scale things vertically and scale things horizontally, which are two totally different concepts. So let's take a look at this graph and see what they're asking us to find. Alright, so it says right now we have a graph right here, and it's saying this is the graph of function f. It says function g is defined as g of x equals 3 times f of x. So here's the concept. Whenever you're taking a function, and we have f of x, if we multiply that by a 3, that is what's called a scale factor. All right? And so we call this, I'm going to call that the a value. So anytime you have an a value, and that a value is being multiplied to the function, two things could happen. If a is greater than 1, which basically means any number that's bigger than 1, it's going to be stretched vertically. So we call it stretched vertically, often also expanded, okay? Stretched vertically, which means it's going to go closer to the y-axis, all right? It's getting stretched closer to the y-axis. Now, if the a value is less than 1, but it is greater than 0, it's going to be called compressed vertically. So that's going to be compressed vertically. It's going to go away from the y-axis. All right? So here's what I want you to understand. When it's stretched, you'll see it go closer to the y-axis. If it's compressed, it'll go further away from the y-axis. And it's only dealing with the y values, really. That's really all you have to worry about is your y values. So if g of x right here, I'm going to go ahead and erase this right here. And I'm going to put g of x in red. If g of x is equal to 3 times f of x, I'm just looking at the y values. So here's my y value right there. It's at a 4. And then I have a y value right here, which is at a 2. And I have a y value right here, which is at a 1. So right now, my y values are at a 4. They're at a 2. And they're at a 1. So all I'm worried about is I'm looking at my y values jumping like 3 times that. So now, from a 4, I'm going to be all the way up to a 12. So I'm going to go, that's what I'm looking for. If I'm at a 2, I'm going to be multiplied that by 3. I'm going to go up to 6. And if I'm at a 1 and I multiply that by 3, I'm going to be at a 3. So I'm going to be looking for a function that goes through these points right here as best as I can. So we're looking for a 12, a 6, and a 3. And that's what it means to be vertically stretched. You'll see that it's clearly closer to the y-axis. Let's see if I can move this. All right. Okay. So the same, now notice, it's going to be the same x values, just different y values. So there's the 12, there's the 6, there's the 3. That's looking pretty good. Yep, B's not it. C's not it. D's definitely not it. So I'm going to go with A. All right, let's take a look at this one. We've got, all right, it looks kind of like a cubed root function here. All right, so let's see what it says. It says function g is a vertically scaled version of function f. The functions are graphed where f is solid and g is dashed. Okay, so f is solid. Now let's take a look at the y values. That's really all I'm worried about. So this y value right here is at a 2. And this y value right here is at a 6. Now, if you want to figure out what your a value is, the a value, or an a times f of x, the a value will always equal whatever the new y value is divided by the old y value. So what is our new y value? Our new y value is a 6. What was our old one? A 2. 6 divided by 2 is 3. So I'm going to say g of x is going to be 3 times f of x. G of x is equal to 3 times f of x. because the y values jumped or scaled up by 3. Scaled up by is better than the word jumped. Oh, there it is. All right, let me try to do that one more time. A couple more here, okay? Let's take a look at this one now. Okay, so here we have a function. There's f of x. It's a logarithmic function. So I'm going to put f of x equals 2 log base 3 of x plus 6. And it says g of x is a vertically scaled version of f. So we got to figure out what g of x is equal to. All right. So let's take a look at our new versus old. All right. What's our new y value divided by our old y value? All right. So it looks like our new one is at a 2 right here. Our old one right here is at a 6. And 2 divided by 6, that is 1/3. So I think g of x is going to be 1/3 of whatever f of x is. So if I say, what's g of x in terms of f of x? That's what it is. Let's see what they ask us to find, though. They ask us to find, they actually ask us to find the actual equations. Let me go back and take a look at this, all right? So let's say we take f of x, all right, let's say we multiply everything by a third. So let's take f of x, which is this, and let's multiply everything by a third. So when you are distributing, you're going to take this 1/3 and you're going to distribute it to the 2, and then you're going to distribute it to the 6. That log base 3 of x is not going to be impacted at all. So a third of 2 is 2/3. So I'm going to put 2/3 log 3 of x, and 1/3 of 6 is 2, because 6 times a third is 2, and this is the function that I'm going to be looking for. So g of x, which is 1/3 of f of x, is going to be this function right here. So I used the scale, I multiplied the scale throughout the function, and I found my new function. So 2/3 log, oh, I think it's a, looks like it's a. Boom. All right. All right. So let's go and do one more, okay? Let's do one more, and then we'll start working on scaling things horizontally. So here we have a function, and it's an absolute value function, and it says f of x equals the absolute value of x plus 3 minus 3. And it says, what is the graph of g of x? So it looks like g of x is 3 times x plus 3 minus 9. Let's take a look at this. G of x appears to be 3 times f of x. Because if I multiply that by 3 and I multiply that by 3, that's how I get this right here. So all I'm going to do is look at my y values, just look at the y values, and I'm going to multiply them by 3. So what's the y value right here? The y value is at 0. So that's going to stay the same. And this y value is at 0. So that's going to, you're like, wait a second, this is -6. That's the x value. So I'm not worried about the x value, I'm just worried about the y value. So I'm at 0 here, I'm at 0 here, so those points are still going to stay the same. But my y value right here is at -3. So this y value is going to shift, like move all the way down here. Not shift, bad word, so I apologize. It's going to be scaled by a factor of 3. So my new function, all right, is going to look like this. That's what I'm looking for. All right. So there's my new function g of x. That's what I'm looking for. Way down here, it went from -3 times 3 is -9, right down there, and then it's going to go up. That's what I'm looking for. And that's it. Nope. Ooh, I like B so far. B looks pretty good. I think it's B. All right. Let's be right, huh? Let's be right. All right, so I'm not going to do any more. This is just basically dealing with this exact same stuff. All we're doing is taking half of this, so half of that y value, half of that y value, half of that y value. We're going to go ahead and move on to scaling functions horizontally, which looks a little bit more difficult. So here's what we're going to talk about. All right, so how do we scale horizontally? For scaling things horizontally, we're dealing with not the y values, we're dealing with the x values, because the x values, remember, x values run left and right. So if we have a function f of x, and I want to scale things horizontally, it's going to be f times, I'm going to call it b of x, where b is what's going to be multiplied to the x. So vertically is very, very, very easy. If I have a number on the outside, just like we had 3, this would be considered scaled vertically by a factor of 3. Scaled by a factor of 3. However, if I have a function here and I'm multiplying it by this value of b, and we're going to talk about two different things, all right? If b is greater than 1, that's going to be different than if b is less than 1 but greater than 0. So here we go. If b is greater than 1, that means it's actually going to be what's called horizontally, we'll call it a horizontal compression or horizontally compressed, okay? Horizontal compression. Also known as something that is shrinking, okay? So those values are shrinking horizontally, all right? So you'll see them compress horizontally. And we're going to look at an example using Desmos. Whereas if b is less than 1 but greater than 0, those are actually going to stretch. All right? Oh, horizontal stretch, my apologies. Call it a horizontal stretch or expansion. Okay, so horizontal expansion. Now, here's the tricky thing, though. It's actually going to be a horizontal compression by a factor of 1 over b. All right? It's actually not a factor of b. It's 1 over b. And over here, a horizontal stretch is going to be by a factor of 1 over b. So what does that mean for us? We're going to talk about what that means. I'm going to pause the video. I'm going to get Desmos ready to go so you can kind of see how it works. All right, so I created a little function here, a little cubic function in Desmos, and I want you to notice this point right here, -1, 2. So our x value is at -1, and right now our b value is at a 1. But look what happens if I make my b value 2. I make my b value 2. All right, what do you notice right there? So now it was at -1, now it's at -1/2. So what happened there? It got, even though that number is a 2 right there, so I'll make sure you understand what I'm talking about when we'll go and write on this, okay? So right now we have what's called f, the blue function there. I have what's known as f of 2 of x. So our b value is 2, but look what happened. It went from -1 to -1/2. What does that mean? That means it was horizontally compressed by a factor of 1/2. Horizontally compressed by 1/2. Where's the proof? It went from -1 to -1/2. So if I'm at -1 and I multiply that by 1/2, now I would be at -1/2, and that's what happened. Okay, so understand, I didn't multiply, I'm not being compressed by a factor of 2, I'm actually being compressed by a factor of 1/2. So let me do it a little bit differently here. Okay, so let's go ahead and do it by, let the b value be a half, and let's see what happens. Okay, there we go, getting closer, right there, boom. Okay, so here's where it was originally, it's at -1, and now I've made the b value a half, and look what happens to our x value. Now it's at, from -1, it's now at -2. So if I have f of 1/2 of x, even though my b value is a half, it's been horizontally stretched by a factor of 2. So it's been stretched horizontally. Just remember, stretching something horizontally means you're going from here and you are stretching it horizontally. So you're stretching it that way. Okay? So horizontal stretches deal with what? Left and right. Vertical stretches deal with up and down. So what are we dealing with here? We're not dealing with the y values. Now we're dealing with the x values. So as I do this, check this out. Notice the y values in this graph stay the same. The y values stay the same. What's the only thing that's changing here when I compress or stretch? I'm compressing or stretching just the x values. I always thought that was kind of cool, like being able to see that. Thank you, Desmos. You guys make things so much easier as a teacher, because I can talk about it all day, but showing students makes it a lot easier. So thank you, Desmos. No, I mean not getting paid for this. I just wanted to let people know I'm very thankful. All right, so let's go back to our problem here. Okay, so let's see if we can find our problem. All right, so check this out. It says function g is a horizontally scaled version of function f. So this is our new function, and this was our old function. All right, so we're going to take a look at the x values. So let's take a look at them real quick. So we were at a 4, and now we're at a 1. So we're on the x-axis, we're at a 4, now we are at a 1. So this looks like it's been horizontally compressed by 1/4, because we're at a 4, and now we are at a 1. So our original x value is here. That's our old one. Okay, and then our new one is right here. It's our new x value. It's at a 1. So I am going to say that g of x is going to equal, hold on, put g of x. G of x equals, we're going to say f of, and we're going to say 4x. Because if the b value is 4, we are being horizontally compressed by a factor of 1/4, or 1/b. All right, so let me take a look right here. So g of x equals 4 times x. So that's why it's going to be this one. Because remember what we talked about. What we talked about was this. Go back over here. If the b value is greater than 1, we have a horizontal compression. And you can clearly see, just like this one, we have a horizontal compression over. All right. Now that's only one of them. I'll go back and we'll go ahead and redo it again. All right, so here we have a couple of exponential functions. All right, a couple of exponential. It says f of x, I'm just going to write it. Since it's blue, I'll write it in blue, equals 2 to the power of x minus 2. And then we have function g over here. It says g is a horizontally scaled version of f. The functions are graphed when f is solid. Okay, g is dashed. It says what is the equation of g? So all I'm going to do, see how they gave us our 2 points here? They gave us our 2 points. All right, and we have, this is at a 3 on the x-axis, and then over here we are at a 6. Okay, so right now, what do we call going from a 3 to a 6? We call that a horizontal stretch. Okay, and when we have a horizontal stretch, we know our b value is going to be less than 1, but greater than 0. So we know our b value, that's going to be right next to the x, is going to be between it? Well, think about this. If I went from 3 to a 6, I know if I do 1 over b, that's going to be our scale factor. It looks like it was stretched by a factor of 2. So if it's stretched by a factor of 2, then we know our b value, if we're stretched by a factor of 2, we know our b value is going to have to be a half. Because 1 divided by a half is 2. So it's kind of hard to see here. Okay, it's kind of hard to see. See how that says a half right there? Okay, it's right next to the x. So our new function is going to be the original, but we're going to put to the power of a half of x minus 2. Because, remember, this is our b value. And when b is less than 1, but greater than 0, we know we are going to have what's called a horizontal stretch. Okay, let's do one more. So we have a function right here in blue. Right now, it looks like we have this value is being multiplied by a half. So our original function says, it's a square root function, equals 3 times the cube root of x plus 4, and now g of x equals 3 times the cubic root of, I'm going to rewrite it as a half of x plus 4. So our b value, once again, looks like our b value is 1/2, but we're going to scale it. It's going to be 1 over b, so 1 over a half, which equals 2, which means we are going to be horizontally stretched by a factor of 2. Horizontal, I'm going to put horizontal stretch. That's not how you spell stretch. By a factor of 2. All right, so what does that mean? That means whatever your x value is, we're going to multiply that sucker by 2. Well, I got an x value right there. That's at 0. Well, 0 times 2 is still 0. But over here, I have a value at 8. Well, if I multiply that by 2, then that dot's going to move from there right over there. So what am I going to look for? I'm going to look for a graph that kind of follows this pattern that goes up. Same y value. See, the same y value at 10, but it's just going to be right there at 16 versus 8, because we're horizontally stretching it by a factor of 2. So what do you need to make sure you have in your journal here? This part right here. Okay, this is huge. So you might want to pause the video and make sure that you understand that if it's greater than 1, it's a horizontal compression. If it's less than 1 but greater than 0, it's a horizontal stretch by a factor of what 1 over the b value is. And that will definitely help you when you are working on these problems. All right, so I'm going to look for a graph that goes through 0, 4 and 16, 10. That's what I'm looking for. Nope. No. Nope. Yay! There it is. All right. There's the stretch right there, all the way to a 16. That stays the same. That's all you got to do. Easy. Not a problem at all. All right. Sometimes I just can't help myself. I just see this. I'm like, I just want to solve it. So you guys see the 2 there, right there? All right. So that's the b value. So if the b value is equal to 2, then we're scaling it by 1 over the b value. So everything is going to be horizontally compressed by a factor of 1/2. So all we got to do is look at the x values and multiply them by a half. So what's the x value right there? The x value is at a 4, so it's going to be at a 2. What's the x value at there? 8. What's half of 8? It's going to be at a 4. And then over here it's at 0. What's half of 0? Well, it's still 0. And so I'm going to look for a graph that looks like this right there. Okay, I'm not going to tell you the answer there, but that's what it would look like. Oh, I'm liking A right now. I'm liking it. I'm liking it. I'm liking A. Totally liking A. Booyah. All right. I'm definitely not going to do this one though, because that would just be wrong if I just kept going. All right. But I will give you guys a hint. This is definitely being horizontally stretched. Okay, by a factor of 2. So that means our b value is going to be half. I'm not going to tell you which answer that is. You'll have a good day.